particular point. Same thing holds true for derivatives. The derivative does not exist at certain points, and you need to be aware of all the different scenarios where a derivative does not exist. Just because we give you a function and we tell you to find the derivative at a particular point, it doesn't mean that you're going to get an answer other than it doesn't exist at that particular point. It might exist at all the other points, but there might be one particular point in f of x where the derivative does not exist. And you need to know the following. A derivative does not exist at, number one, a corner. A derivative will not exist at a corner. This is where the one-sided derivative, derivatives differ. In other words, if you find the derivative from coming in from the left and the derivative from the right, if they're different, then the derivative does not exist at that point. A good prime example, look at the function of the absolute value of x. We all are familiar with that graph. This point right here is called a corner. And I know that a corner has been formed because clearly the slope of this piece of the absolute value function has a negative slope. And this side here, of course, the line slanting upward, it's got a positive slope. When the one-sided derivatives differ, and they definitely differ here, one's negative, one's positive, at that point right there, there is no derivative. That's called a corner. Number two. A cusp, C-U-S-P. The derivative of a function does not exist at a cusp. Would it help you if you had a stylus? Well, you got one. I just kept forgetting to offer. Okay, a cusp. This is where the slopes of your secant line lines, plural, approach infinity from one side and approach negative infinity from the other. We sometimes refer to the cusp as the extreme case of a corner, the extreme case of a corner. Good example, consider the function f of x equals x to the 2/3 power. The graph of this function, probably not familiar with this one. Looks like that. Where the slopes of the secant lines approach from one side and approach negative infinity from the other side. In other words, my slopes of the secant lines are going to be approaching positive infinity, a negative infinity. Some people have difficulty telling the two apart, the difference between a corner and a cusp. Please note, the only way that you're ever going to get a corner is if it is formed by straight line segments. And if you have curves, then you have a cusp. Now the problem is when one side is a straight line and the other one's a curve, I don't know what we call that, cuspy corner, I don't know. But the derivative wouldn't exist there either, okay? Number 3, I always have trouble with this one. A vertical tangent. If you have a vertical tangent line at a point, the derivative does not exist at that point, at a vertical tangent line. This is where the slopes of your secant line approach either infinity or a negative infinity from both sides. And a prime example of a function that would have a vertical tangent line is the cube root of x. Now the graph of the cube root of x, you should know this one. Kind of reminds me of the graph of the tangent function. And my tangent line is that vertical line there, and it intersects the graph. That's why I said I really have trouble with the concept of a vertical tangent line. But anytime you've got a curve resembling this, you're going to always have a vertical tangent line, and therefore the derivative doesn't exist. And then number 4, at a discontinuity. Any place the function is discontinuous, the derivative won't exist. If you've got a hole, a jump, a gap in your graph, at that point the derivative does not exist because the function is not continuous at that point. Okay? If you have a discontinuity which will cause one or both of the one-sided derivatives to be non-existent. F of x is equal to a negative 1 if x is less than 0, and a positive 1 if x is greater than 0. Piecewise function is discontinuous at x equals 0. Therefore, the derivative doesn't exist at x equals 0. So know these 4: a corner, a cusp, a vertical tangent line, or a point of discontinuity. A corner, a cusp, a vertical tangent line, or a point of discontinuity are the 4 places where a derivative at a point will not exist. Also with the concept and the idea of differentiability, I just like that word, differentiability. On your assignment, you will be given a function, and we will ask you to determine if the derivative exists at that point. You did that on today's homework assignment, so real quick like, show that the function is not differentiable at x equals 0. And we give you the function piecewise, x cubed where x is less than or equal to 0, and 4x where x is greater than 0. So I've got to take the limit as x approaches 0 from the left of f of x, which is going to give me f of x minus f of 0 all over x minus 0. So I've got the limit as x approaches 0 from the left of x cubed, function value 0 all over x minus 0 gives me the limit as x approaches 0 from the left of x squared, which gives me 0. The limit as x approaches 0 from the right of the function f of x is going to give me 4x minus 0 over x, which gives me the limit of 4x over x, which is equal to 4. So I conclude that the right and left-hand derivatives are not equal. Therefore, f of x is not differentiable at x equals 0, or any other way that you want to state that. I know it looks kind of, or some of you are thinking, well, how ridiculous, why on earth, I mean, I see this, so why do I have to do that? I mean, anybody can tell if the two aren't the same, then there's no derivative there. But for the College Board, you got to give it, you got to write it. If you stopped right here with your left and right hand derivatives and didn't conclude, draw closure to the problem, you wouldn't get any points. You wouldn't get any points. So extremely important to remember that. Most of the functions that we encounter in calculus are differentiable wherever they are defined, which means that they will not have corners, they will not have cusps, they will not have vertical tangent lines, and they will not have any points of discontinuity within the domain of that function. And as long as that's all true, then the function is said to be differentiable. The derivative will exist wherever you want, as long as you pick a point in the domain of that function. Their graphs will be unbroken and smooth with a well-defined slope at each point. One thing with respect to differentiability, differentiability implies local linearity. Differentiability implies local linearity. A good way to think of a differentiable function is that they are locally linear. In other words, if I've got a function I graph this function, it looks something like that. It's really funky looking. But it appears to be a continuous function, of course. And what we're saying is that differentiability implies local linearity. And all that means, if you pick a point on this funky graph anywhere, let's pick an obvious one. And clearly the curve is, or the graph is curving at that particular point. It looks like a curve. But if you were to magnify that point over and over and over and over again, at this particular point, it would appear to be straight. It would appear to be linear. And if we localize in on a given point, then we are locally linear. That's all that's saying at any given point. It says, in the jargon of graphing calculators, differentiable curves will straighten out when we zoom in on them at a point of differentiability. And you can do that. Give yourself a graph that's really curvy, pick a point, and then start zooming in on it with your graphing calculator, and eventually your graph will look like a straight line, locally linear. Just remember, I love you, and I don't want you to be mad at me about what I want to share with you next. Let me show you how to find the derivative of a function at a point using a graphing calculator. Not the definition of a derivative, not that nasty, crazy, awful, different quotient. Oh. A graphing calculator will find the derivative of a function at a point. Many graphing utilities can approximate derivatives numerically with good accuracy at most points of their domains. For the small values of h, the difference quotient is often a good numerical approximation for the derivative at a point. However, the same value of h will usually yield a better approximation if we use something called the symmetric difference quotient. And it is f of a plus h minus f of a minus h all over 2h. This is called the symmetric difference quotient. You'll never need to know that, okay, so don't worry about it. And I mentioned the symmetric difference quotient because that's what your graphing calculator has been programmed to do, okay, to find numerical derivatives. And this is what our graphing calculator uses to find the numerical derivative. The numerical derivative of a function as donated by Ender, the numerical derivatives will compute in this book. They're going to use the value of h equal 0.001. Our calculators are programmed to allow that value of h, where you take f of a plus h minus f of a minus h all over 2 times h. We're going to let h be equal to 0.0001. No, 0.001. So let's go back to today's assignment, and let's pick one. It looked horrible. Well, they all look kind of bleh. Didn't have to find any for sure. Oh well, what the heck. No, I lost my chalk. I'm just so excited that I can't hardly contain myself. Here's the problem that I want to work. We'll keep it simple. I want to find the value of the derivative when x is equal to 2 if the function f of x is equal to x cubed. Math 8 is going to be your rock. So you turn your graphing calculator on. After you turn the TV back on. Everybody knows where your math key is on your graphing calculator. So when I hit the math key, I see fractions and decimals and cubes and cube roots and x roots and f minimums and maximums. So let's scroll to number 8, math 8. You will remember math 8, trust me. So when I hit the 8, now if your calculator does not show that, if your calculator shows ender left parentheses, your calculator is operating on an old operating system, and I need to update your calculator because I want you all to have that because that is so perfect. The first thing that you have to do is tell the calculator with respect to what variable are you finding a derivative, and it's always going to be with respect to the variable x. So enter the variable x. So I want to find the derivative with respect to x of, well, what's your function? Well, in this case it's x cubed. So we go x cubed. And then there's that vertical bar again. That always tells the calculator, or even when you're working, that I'm going to evaluate this derivative at x equal, well, I want x equal 2. And I hit enter, and I get 12.000001. This is an approximation. It's not the exact value. We have worked this problem on the board for you using the difference quotient, and we found it to be equal to 12. The calculator just gave me 12.000001. We are accurate to 5 decimal places. Friends, that's pretty good. That's pretty good. So now, anytime we ask you to find the derivative of a function evaluated at a point, math 8 is all you're going to do. You're not going to have to use a half a sheet of paper using the limit as h approaches 0 of your difference quotient that you usually mess up because of the algebra part. Now we've got a tool that will do it for us. It will do it for us. Try this one. I want to evaluate the derivative of the following function. If f of x is equal to the absolute value of x, find f prime of x. At x equals 0. Okay, we can do this. So I'll clear that out. Again, math 8. And that brings up your numerical derivative icons. Again, I'm going to differentiate with respect to the variable x. And my, oops, went too far. My function is the absolute value of x. So you can go into catalog and get your absolute value, or you can go into math, calculate, or excuse me, math number. And number 1 is absolute value. I like that one. It's quicker. So the absolute value of x. And what do we want x to be equal to? 0. Enter. The value of that derivative is equal to 0. Not. Now come on, what did we just do? We looked at this graph right here, the absolute value of x. It's got a corner at x equals 0. The derivative does not exist at x equals 0. You gotta be smarter than your calculator. It doesn't differentiate where there are corners and cusps and those kinds of things. Make sure you know what your function looks like that you're trying to differentiate and evaluate at a point. Because it's going to give you the wrong answer sometimes. So you got to be smarter than your calculator, okay? Smarter than your calculator. We kind of hinted on this just a moment ago, but differentiability implies continuity. Differentiability implies continuity. And I know for a fact that this particular statement was required on 2 different problems on the AP exam from last year. The fact that if a function is differentiable, you can conclude that the function is continuous. Differentiability. It's a fact, Jack. Don't forget it. If the function is differentiable, you can also conclude that the function is continuous. But the converse of that statement is not true. In other words, if I have a continuous function, then I know it's differentiable? No, that's not true. In other words, consider the graph of this function here. Is it continuous? Oh, absolutely. But is it differentiable? No. Differentiability implies continuity, but the converse is not true. Continuity does not imply differentiability. Please remember that one. Intermediate value theorem for derivatives. Very similar to the intermediate value theorem for continuity. Basically, it says if A and B are any 2 points on an interval for which the function f is differentiable, then we can conclude that the derivative takes on every value between f prime of A and f prime of B, the intermediate value theorem. If you remember, the intermediate value theorem for continuous functions said that if you have a function that is continuous on a closed interval, the function will take on every value between f of A and f of B. In other words, a continuous function cannot skip values. Intermediate value theorem for continuity. Now we've got the intermediate value theorem for differentiability. Your homework assignment for Monday.